I'm Lawrence Forsley. I'm pleased to be a plenary speaker at ICCF-23 and with my colleague, Dr. Pamela Mosier-Boss, happy to discuss conventional fusion in an unconventional place. First, an outline. I'll go through an introduction of terms, conventional fusion, fusion in an unconventional place, electron screening and modeling, palladium-deuterium codeposition protocol, conclusion and acknowledgments. The takeaway I wish to leave you with is fusion does occur in unconventional places. Fusion modeling is important, and the palladium-deuterium codeposition protocol works. So first, an introduction of terms. Cold fusion, or the Fleischmann-Pons effect, was originally misnamed by the press. LENR, or low-energy nuclear reactions. LANR, lattice-assisted nuclear reactions, as coined by Mitchell-Schwartz. Condensed matter nuclear reactions, or the Journal of Condensed Matter Nuclear Science, edited by Jean-Paul Barbarian. And then there's lattice confinement fusion, coined by Nee and others and appropriated by myself. And as Scott Adams noted, this is a hard thing to sell, and it has been. So conventional fusion. We have ICF, or inertial confinement fusion, laser fusion an example. MCF, magnetic confinement fusion, such as a tokamak, and LCF, lattice confinement fusion, LANR, Fleischmann-Pons effect. And then I'll discuss the Lawson criteria and the fusion triple product. So fusion comparisons. Laser fusion, such as Omega over on the far right, has a very, very small 100-micron core. Magnetic confinement fusion, or tokamaks, as ASDEX, which is as large as 7 meters or larger with ITER. And then we have lattice confinement fusion, or palladium-deuterium codeposition, and I have a cell from CODEP that you see there. What's important about these is the density of the ions per cubic centimeter, the ion temperature, the active radius, and the confinement time. And the two that really work together are the density and the confinement time, ranging from 10 to the 26 ions per cubic centimeter with laser fusion, but only for nanoseconds, versus a density of 10 to the 14 with magnetic confinement fusion, which will hold it for seconds or perhaps longer. We fall between these, but there are other side effects too. The Lawson criteria and the fusion triple product. So John Lawson in 1955 looked at how one would go about building a useful thermonuclear reactor, taking into account plasma heating, the ion density, the fusion cross-section, and temperature, and then looking at the energy losses from Bremsstrahlung and from neutrons leaving. Later, the fusion triple product was coined to come up with a more efficient way of looking at this. So we have a plasma density N, a plasma temperature T, and an energy confinement time tau sub E. And even in 55, Lawson quoted saying, even with the most optimistic possible assumptions, it is evident that the conditions for the operation of a useful thermonuclear reactor are very severe, which has led many wags to note fusion has been 20 years in the future and always will be. Now, next, look at fusion in an unconventional place. First, look at the Fleischmann-Pons cold fusion confusion, why LENR fails, and when LENR succeeds. As my colleague Pamela Mosier-Boss noted, it's neither cold nor necessarily fusion, but it is nuclear. And Julian Schwinger, Nobel laureate in physics, wrote, unlike the near vacuum of hot fusion, the ambient environment of cold fusion is the lattice, which is a dynamical system capable of storing and exchanging energy. And as this cartoon shows, this could be the discovery of the century, depending, of course, on how far down it goes. The original Fleischmann and Pons approach involved having heavy water, D2O, with an anode and a cathode, and the cathode was made of palladium. And there are at least 7 ways this could fail. One is an improper cell configuration. Another is unknown palladium cathode history, the insufficient incubation time, insufficient loading, insufficient aerial current, which would give rise to a low deuteron flux, the controlled temperature, which has to do with calorimetry. If you want to have accurate calorimetry, you have a constant temperature bath, but it prevents the system from becoming highly exothermic. And then finally, if you went looking for conventional fusion neutrons, as my one-time boss said, there is a dead graduate student problem. There are none. If you're producing fusion at the power outputs claimed, then you'd be flooding the room with neutrons. When Leonard succeeds, there are at least 5 supporting conditions. The plot to the left shows superabundant vacancies where there are missing palladium atoms in the unit cell. These may also be nuclear active environments, or NAE, but the key is to host a high-density, high-flux hydrogen isotopes. Another possible way of driving these reactions is ferromagnetism. Palladium unit cell is nominally paramagnetic, but if you constrain the lattice, it can become ferromagnetic. And another aspect is electron screening, which modifies the astrophysical factor S sub E and the gamma factor. And the plot to the left shows if you go from bare deuterium fusing with a very small cross-section to even as little as 310 eV, you can get 10 orders of magnitude improvement. If you can increase it to 3.5 kilovolts of electron screening, you can get 20 orders of magnitude. And finally, there is the work of Peter Hagelstein with phonon-nuclear coupling to both drive reactions and to shed the energy without producing fast neutrons. Now discuss electron screening and modeling, stars and metals, nuclear modeling, nuclear reaction modeling, density functional theory modeling, and the condensed matter fusion triple product. So stars and metals have something in common. They both have degenerate electrons. And in fact, in the case of white dwarf stars, this is what holds them up. This appears in gas giant planets, and it's in metals in the conduction band. Hence, it's also involved with LCF and deuterated lattices. The Lawrence Berkeley National Lab published papers in Nature and Applied Physics where they attributed a 100 to 1,000-fold increase in fusion rates due to electron screening at only 1.2 keV center of mass deuterium energy. And again, screening is effective only below 10 keV. The plot to the right-hand side shows that LCF embraces all the way from room temperature, 10 to the minus 2 eV, out to 10 keV, and hence is also laboratory astrophysics. In terms of nuclear modeling, we've used a variety of products, including MCMP and GANT4. We've written our own neutron unfolding codes and pulse shape discrimination. We've used SRAM and TRAM to track ions, as well as track test and p-test, which track alphas and protons, specifically in CR39, solid-state nuclear track detectors. And from these, we can do a linear energy transfer analysis. The figure to the right shows a synthetic depleted uranium fission gamma ray spectra where you can see 2 particular fission products that have appeared. The lower left-hand side, we have particle propagation with the VisEd visual editor. And then to the right, we have an example of SRAM-TRAM modeling alpha particles going into CR39. The problem we have with nuclear reaction modeling, though, with both MCMP and GANT4 and SRAM-TRAM, is MCMP and GANT4 will not model fusion reactions for charged particles below 1 MeV. And most of the fusion reactions occur between 1 and 100 keV. Electron screening is only applicable below 10 keV. SRAM and TRAM will model ions in these energy regions. However, it doesn't model nuclear reactions. Which brings us to density functional theory modeling. And we're looking here at both strained and unstrained palladium deuterium lattices. The upper section is zirconium oxide with palladium deuteride embedded within it. The lower one is magnesium with palladium deuterium oxide. And what's interesting is they both give rise to an electron charge density. However, electron spin polarization, which gives rise to magnetization, occurs with the zirconium oxide, which strains the palladium lattice, but it does not occur with the magnesium oxide, which does not strain the lattice. And this, in fact, is in keeping with what Iomura observed, both in the case of zirconium oxide and with 2 others, but not with magnesium oxide. Hence, we have a strain-induced ferromagnetic LCF driver. So looking at the condensed matter fusion triple product, again, the fusion triple product consists of three terms: the plasma density, the plasma temperature, and the energy confinement time. So in condensed matter nuclear reactions, we refer to them as globally cold but locally hot. An example being the picture to the right of a microphotograph where we've actually vaporized some palladium, but the lattice is intact around it. And indeed, elemental anomalies are found around the rim. So we don't have Bremsstrahlung losses because we're not that hot. And we have very few fast neutrons, hence little mass or kinetic energy loss. We have a very high plasma density, in the order of 10 to the 29 ions per cubic meter. The effective cold plasma ion temperature, due to screening, is on the order of 3.5 kilovolts. And this has actually been measured with accelerator experiments. The confinement time is a little more difficult. It's a function of the deuteron diffusion versus octahedral to tetrahedral hopping versus sound speed. But it's been measured and inferred somewhere between 10 to the minus 5 seconds and effectively infinite. So I've adopted 10 to the minus 3. So now comparing the triple product comparisons across three forms of fusion: magnetic confinement fusion at the Joint European Torus in 1990, they have a value of 9 times 10 to the 20. And then we have the same with the Japanese Torus 60U experiment in 2018, which is increased to 1.3 times 10 to the 21st. As comparison with LCF palladium deuterium condensed matter, beginning before the announcement in 89 and right through to the present, on the order of 3.5 times 10 to the 26th, orders of magnitude larger. What's important is even if you reduce the screening by a factor of 10, down to 350 eV, and you reduce the confinement time 1,000 times to 1 microsecond, we still come up with a value of 3.5 times 10 to the 22nd. Again, the deuteron cold plasma density is what makes up for this. Now I'll talk about the palladium deuterium codeposition protocol. First, it's an alternative. Second, I'll show the Science Channel Brink video. Then look at solid-state nuclear track detectors like CR39, and discuss university students, and finally some of our publications. So the alternative, unlike the standard method, is we actually co-deposit palladium and deuterium, reducing both metals together, onto a cathode. And as a result, it starts off already expanded, and we get an instant loading approaching unit stoichiometry without cracking. As the microphotograph shows, it's a fractal high surface area. There are many lattice defects and consequently probably a lot of superabundant vacancies. Once the codeposition is over, we increase the current, the D plus flux goes up, and the reaction begins. And this can happen as little as a few days. US patent was granted in 2013 on this. And now I'll show a video that discusses how this works.
Nuclear physicist and senior science advisor at the US Department of Energy, Dwight Williams. Dwight, what exactly have these researchers done?
Well, it's pretty simple when you think about it. They took some electrodes, some nickel or gold electrodes, put it in a solution of palladium chloride mixed with heavy water. That's actually D2O instead of H2O. They ran a current through it, and the output that they got on their CR39 detection system indicated the evidence of neutron generation. And of course, neutrons are clear evidence of fusion.
So the solid-state nuclear track detector, or CR39, that he showed is a polyallyl diglycol carbonate, otherwise known as PADC, and it consists of a monomer that's been polymerized, which is a C12H18O7, and you can see the chain in the picture to the right. This has been widely used in laser fusion on the International Space Station and in codeposition. It has a very high efficiency for detecting charged particles. It has a very poor, less than 10 to the minus 3 efficiency for detecting fast neutrons because they have to recoil off of the oxygen, the carbon, or the hydrogen in the PADC. And this is, again, widely used for commercial and research neutron and alpha dissymmetry. And what we do is we etch this in a lye solution, basically 6 to 6.5 molar sodium hydroxide, for anywhere from 3.5 to 7 hours, depending on the temperature. But what this does, it makes the tracks visible, and we can then analyze these and do a linear energy transfer analysis of them. That analysis was done for three co-deposition replications at SRI. On the left-hand side, we're looking at primarily fast protons, alphas, and some neutron recoils. On the right-hand side, our Russian colleagues looked at fast neutron recoils and compared them with californium-252, which is a neutron source. There are several different species here indicating very different reactions that have occurred. And so there are several nuclear charged particle and neutron exit channels available. On the right-hand side, we notice that CODEP is essentially a monochromatic 2.5 MeV neutron source. So on the basis of this, we had university students at the University of California, San Diego, 3 successive years of chemical engineering undergraduates who, among other things, compared copper and palladium-D electrodeposition, found tracks only with the PDD, and then presented this work at 2 conferences, one in Sicily and one at the American Chemical Society in Salt Lake City. On the basis of that, Pamela and I wrote a paper, Energetic Particle Emission in PDD Co-Deposition, an undergraduate research project to replicate a new scientific phenomena. And this has been viewed or downloaded over 3,500 times. Among the publications, this appeared in the British journal New Scientist with a quote from Dr. Johan Frenzy looking at the data, which you saw a moment ago in the Science Channel Brink video, where the triple tracks appear. And some of the co-deposition publications we've had, including in 2009, our paper on triple tracks in CR39 as the result of PDD co-deposition and evidence of energetic neutrons. And this was published on the 70th anniversary of nuclear fission, published in the same journal in 1939. And you'll note over on the left-hand side that we see the 3 tracks coming off, the alpha particles from breaking up carbon-12 in the CR39, and this is the hallmark of DT fusion. This has been a collaborative effort. We've had 60 published refereed papers in 21 journals over 32 years. We have 60 authors and co-authors from 14 countries. There are 3 more journal papers accepted. 15 of these papers are co-deposition replications. 17 discuss modeling and theory. 17 are on thermal effects, and 42 are on nuclear emissions. In 2020, Elsevier published a book on cold fusion, edited by Jean-Paul Barbarian, and there is a chapter on PDD co-deposition. And as we've traveled around, we've run into a number of people like Martin Fleischmann, Vittorio Vellante in Italy, and Francesco Celani in Italy, Pierre Carbonell actually setting up a cell to run in Belgium. I came across a border guard in Germany who was more than a little puzzled. His has been used at KAIST in South Korea and in the U.S. with us at SPEWAR, and then also at TASL, the people who make our CR39 scanner. And what's interesting is that Martin and Stan Pons had considered using PDD co-deposition, but they thought it would be too difficult, so they instead went to bulk loading of foils and wires with deuterium. So in conclusion, condensed matter nuclear reactions, though unexpected, they do exist. And the particles have been detected. Charged particles, neutrons, activation and transmutation products, excess power. Co-deposition is reliable, repeatable, and safe. Multiple university students have used it. And as they say in the business, not even the sky's the limit. And I'll let Martin Fleischmann have the last word.
A very interesting discussion. I think it is the status is as before. We know a lot more about the system, but not enough. Not enough to bring it to any satisfactory conclusion. So, keep going.